Good morning. Hope everybody's doing all right today. So we are going to pick up where we left off in section 1.6. We got through part of example 2, so we'll finish up the second part and then continue from there. The plan for today is to probably finish up 1.6, maybe even get into 1.8. Whatever of 1.8 we don't get through, we should be able to finish tomorrow. And then I'm also hoping to have some time to review for the test tomorrow also. So don't forget, the test does open at midnight tonight. You just have to choose a 2-hour window to sit down and take it sometime between then and Friday at midnight. So feel free, if you want to go ahead and take it, if you feel good about the material, you can start it at midnight tonight. If you want to wait until after we review tomorrow, that's also fine, so long as you get everything done before midnight on Friday, okay? Also, don't forget there is the homework on 1.5 through 1.8 that's due by midnight tomorrow night, Thursday night. So make sure that you're working on that. Let me know if you've got any questions. I think that's all for now from me. So any questions, comments, concerns before we get started? Yeah, Paulina.
I'm sorry, I just logged on. I just had a question. So the test is still scheduled for Friday?
Yeah, so it'll open at midnight tonight, and then you just need to find 2 hours between then and Friday at midnight to take the test.
Great, thank you.
Yep. Any other questions? Just a reminder, right? You have a 2-hour window to take it. That doesn't necessarily mean it'll take you the full 2 hours, right? So, plan on having that 2-hour window just in case you need it. But if you finish early, you can log out just like you did with the Respondus Lockdown browser tutorial. Okay. All right. If you think of anything else, please feel free to ask. I'll be happy to answer any questions you got. And again, we will definitely spend some time going over the practice test tomorrow once we get through 1.6 and 1.8. Okay. All right. Part B. Okay. So we're going to use those limit laws that we looked at yesterday. We're going to split this thing up, and then we're going to try to evaluate this limit. So let's think about our limit laws and what we can do first here. So what's one thing we could do with that function? Hyro?
Since we're dividing, we know we can have a 0.
Okay, good. So we know we can't have a limit that's equal to 0 in the denominator, right? Now, in this case, we want to split everything up first, and then we can check for any of those limits that might give us 0. And then if we get one, then we know it doesn't exist, right? But let's try to split everything up first before we look at that. So what could we split up here? Okay, so when you say each one, what do you mean each one? Okay, the equation, then what's inside the equation? Still not quite sure exactly what you're referring to in terms of finding the limit now. Okay, go ahead.
Okay. So we have to separate like x cubed plus 2x squared minus 1. That can be like its own limit at one point, and then the other one, 5 minus 3x, is its own limit.
Okay, all right. So you just want to separate the numerator and denominator into two separate limits. Is that right?
Yeah.
Perfect. All right, so let's do that. So we're going to take the limit as x approaches -2 of the numerator, x cubed plus 2x squared minus 1. And then we can divide that by the limit as x approaches -2 of 5 minus 3x. Good. All right, so that's one of our limit laws, right? Is if we have division, we're allowed to split up that division into two separate limits. All right. What else can we do now? All right, good. So we can break it up even further now, right, into each of its terms. Because remember, our addition and subtraction we're allowed to split up also. So let's go ahead and do that. So in the numerator, I'm going to take the limit as x approaches -2 of x cubed. Then I'm going to take the limit as x approaches -2 of 2x squared. And then subtract the limit as x approaches -2 of 1. So just splitting up the addition and subtraction in the numerator. Then we can do the same thing in the denominator. We're going to have our limit as x approaches -2 of 5 minus the limit as x approaches -2 of 3x. Okay, so we split up our division first, and then we can split up all the addition and subtraction in the numerator and the denominator. Are there any other laws of limits that we could apply to this one now? Okay, good. Anytime we have a constant inside of a limit, we know that's going to be equal to the constant, right? So we have two of those, the limit of 1 and the limit of 5. We know those are just going to be the constants. Anything else we can do at this step? Okay, since we have a constant in front, we can bring, okay, so in each of these, I'm looking at this limit here and this limit here. Okay, we have those coefficients in front of our x variables, right? Those can be brought to the front, right? So make sure you do that. I'm going to rewrite this now. Keep the limit as x approaches -2 of x cubed. Plus, I'm going to bring out the 2 from this limit. So 2 times the limit as x approaches -2 of x squared. Then we're going to have minus, and we already said that limit as x approaches -2 of 1 should just be equal to the constant. So that's just going to be a 1 over. We have this limit as x approaches -2 of 5, which should just be equal to 5 now. Minus, and then this 3 we can bring in front of the limit. So we're going to have 3 times the limit as x approaches -2 of x. Any questions on that step? All right, now once we get it to that point, and now if you think back to part A, when we got it down to where it was just x's to some power inside of our limits, what did we do at that point? Yeah, now we can just substitute, right? So we can just take the -2, we can substitute it in for x. So this first limit here is just going to give us -2 to the third power, plus we have 2 times the limit as x approaches -2 of x squared is just going to be a -2 squared. And we have our -1. That's all going to be over 5 minus 3 times this limit, and we're just going to substitute -2 in for x. So that just gives us that now. Any questions about how we got that? Now, once we've gotten rid of all of our limits, now we can just simplify that. So I'll let you go ahead and put that in the calculator. Let me know what you get once you simplify it all. Yeah, Dean, technically, I mean, if you wanted to write in one additional step there where you actually pull out the exponents, I'm kind of combining that step because we're really going to substitute the -2 in for the x and then raise it to the third power. But yeah, if you wanted to, you could technically say it's like this thing raised to the third, this thing raised to the second, right? And then the last one is just the x, so you don't have to worry about that. Okay, but yeah, if you wanted to put a step in there where you're bringing it down just to a limit of x and then raise to that power, you could do that step too. All right, good. So once we simplify this now, we should get -1 over 11. Okay, so this would be our final answer now. Any questions on part B there? Okay, now I want you to look at both of these and see if there's an easier way that we could have found both of these limits. So looking at what we did for the work in part A, what we got it down to, same thing in part B, we could have just substituted, right? Because if you look at the last step in both of these cases, right, like this one right here and this one right here, all we've done in part A is we've taken a 5 and we've substituted it into this function right here, because it just becomes 2 times 5 squared minus 3 times 5 plus 4. That's what we get down here now. Same thing with this one, right? If we just substitute in the -2, we get -2 to the third power plus 2 times -2 squared minus 1, that's the numerator, over 5 minus 3 times -2. That's just substituting -2 into the function itself. Okay, so that's where we're headed now, right? Rather than having to constantly use these limit laws and write out all of these steps, we know now for these two particular types of functions, right? So we're only looking at polynomial functions and rational functions right now. We are allowed now to just direct substitute, if possible, to find our limit. Okay? Now, you won't always be able to do that because remember in the previous section, we had some that would give you 0 in the denominator. In those cases, you can't just direct substitute. But if you can and you don't get an undefined answer, now we're allowed to do that with polynomials and rational functions. Okay? Any questions there? All right, and that's what this next slide tells us. So if f is a polynomial or a rational function and a is in the domain of f, then we can just say that the limit as x approaches a of f of x is just equal to f of a. In other words, we can just take that a value, substitute it into our function, and that will tell us what the limit's going to be, as long as it's defined there. All right, now let's take a look at this one. So now we want to find our limit as x approaches 1 of x squared minus 1 over x minus 1. So first off, what type of function do we have this time? So this is where we have to think back to those different types of functions that we looked at early on in this unit. So what type of function would we call that? Good, it is rational, right? So anytime you have a polynomial in the numerator, polynomial in the denominator, we call this a rational function now. Now, remember on the previous slide, we said as long as the value that we're approaching is in the domain of the function and it's rational, we can direct substitute. Can we direct substitute this time? No, right? In this case, 1 is not in the domain of that function because that's going to give us a 0 in the denominator. So we've got to find another way to actually find this limit now. Now, one option is obviously to go back to what we did in the previous sections and just create a table of values, get closer to 1, and figure out what that limit is. But we can also try simplifying the function first and then seeing if we're able to direct substitute at that point. Okay, so is there anything we could do to this rational function to simplify it. We can try factoring, right? So let's look at our numerator here. I'm going to rewrite this now. Limit as x approaches 1. If we were to factor the numerator, what would those factors be? Good, right? It's a difference of squares, and we're going to get x plus 1 times x minus 1. Now, the denominator, x minus 1, there's nothing we can do with that, so I'm just going to leave that as x minus 1. Now, looking at what we've got there now, can we simplify that? Yeah, right? We have a common factor in the numerator and denominator. Those common factors are going to cancel out. So if I cancel out the common factor of x minus 1, now we're left with the limit as x approaches 1 of x plus 1. Any questions up to that point? Okay, now once we've simplified, can I direct substitute now? Right? Now we have a polynomial function. 1 is definitely in the domain of that function, so now we're allowed to direct substitute. So if we do that, what's that going to give us? 2. Good, right? So we just plug in the 1 for the x, we get 1 plus 1. That's equal to 2, and that is our limit now. So even if the original function, the value you're approaching, is not in the domain, see if there's a way that you can simplify that function first, because a lot of times you'll be able to do that, and then we can still direct substitute. Any questions on that limit? All right. Now, if f of x is equal to g of x, so we got two different functions equal to each other, whenever x is not equal to a, then the limit as x approaches a of f of x is going to be equal to the limit as x approaches a of g of x, provided that the limit exists. Okay, so basically, as long as these two functions are the same function everywhere except for that one particular x value, then we know the limit as x approaches that x value is going to be the same for both functions. You can see that in this graph down here. So basically, we've got this line f of x with an open circle right here. This one over here, same thing, but this one's defined at this point up here now. So that's the only difference in the two functions. Well, as I approach that a value, which in this case is 1, from the left and the right, in both of these functions, f of x and g of x, I'm still approaching 2. Okay, so both of those would have the exact same limit at a, even though they have a different defined value at 1, at that a value. This is true no matter what the functions look like to begin with, right? So if they just have that one point, right, that has a different defined value, the limit as we approach that value is still going to be the same for both. All right, so let's take a look at this limit now. We want to find the limit as x approaches 1 of g of x. G of x is a piecewise function now, where it's equal to x plus 1 if x is not equal to 1, and it's equal to pi whenever x is equal to 1. Now let's think about what this graph looks like, okay, because I think that'll be helpful in thinking about the limit here. So if we were to actually sketch this graph, what do we know about this graph? All right, good. So we have a linear function defined for the first part, x plus 1. What do we know about the x plus 1 then? So in terms of its graph, what information do we have there? Okay, good. Slope of 1 and the y-intercept is going to be 1, right? So I'm going to start here at 1, my y-axis. And then if we have a slope of 1, we're going to go up 1 over 1 to the right. But if we do that, what do we know happens at x equals 1? Okay, good. There's going to be an open circle there because it's not defined for the line at that point. It's actually defined at pi for 1. So I need to go up here to like 3.14 and put that circle. But everywhere else except for 1 is going to be this line right here. We're going to have this graph. So y-intercept of 1, slope of 1, open circle at x equals 1 because it's defined as pi at that specific point. Now, what we're trying to find is the limit as x approaches 1 of our function. Well, what's the limit as x approaches 1 going to be equal to then? 2. Good, because remember, we only care about the value that we're approaching from the left and the right, not the actual defined value of the function there. And so this limit is going to be equal to 2. And this goes back to what we just saw on the previous slide, right? As long as that function is x plus 1 everywhere except for that one specific value, we can really, in this case, just say that the limit as x approaches 1 of g of x is equal to the limit as x approaches 1 of x plus 1. And now we can direct substitute and get 1 plus 1, which is equal to 2. Since this function is defined as x plus 1 everywhere except for 1, when we're finding the limit at 1, we can still just direct substitute into the top part of that piecewise. Any questions on that one now? All right. So now we've got the limit as h approaches 0 of 3 plus h all squared minus 9 divided by h. All right, so first things first, if we can direct substitute, that's what we want to do right off the bat and we'll be good, right? Can we direct substitute this time? No, right? If we do that, we're going to get 0 in for h in the denominator, right? We can't have 0 in the denominator, so we can't direct substitute. So again, like that other example, we want to see, is there a way we could simplify this first, and then maybe we could actually direct substitute at that point? So is there anything we could do with this function to try to simplify it first? All right, good. Let's go ahead and expand out what we've got, the 3 plus h squared. Keep my limit as h approaches 0 here. If we expand 3 plus h squared, what's that going to give us? Good, right? So we get 9 plus 6h plus h squared. Then we still have our minus 9, so bring that over, and this is still over h. Any questions on that step? All right, now, what can we now do with that numerator? Okay, good. We have a common term here. 9 and negative 9 are going to cancel each other out. So if we combine like terms, we're left with 6h plus h squared all over. Good. Now we have a common factor of h in the numerator that can be factored out. So we're going to go ahead and do that. So we've got the limit as h approaches 0 of h times 6 plus h all over h. And now what can we do? Good. Now the h factor in the numerator and denominator is going to cancel out, and we're left with the limit as h approaches 0 of 6 plus h. Once we get it to that point, now what do we do? We can substitute. Good. So if we direct substitute in here, that's just going to give us 6 plus 0. So our limit's equal to what this time? Just 6. Perfect. Yeah, Hiro.
So when we're doing this, do we always have to carry like the limit side, like on the left side until like we get to the substitution part?
Technically, yes, right? Because to make it actually equivalent to the previous step, you need that there. If you drop it, right, as you're working through a problem on a test or something, I'm probably not going to take off points, but be careful because it is very easy if you forget to write it down to then forget to actually take the limit when you get down. So like, if you had dropped it and you got down to this, a lot of people would leave this as their answer. So just be careful, okay? I'm not going to take off points if you don't write it, but make sure that you're actually taking the limit when you get down there, okay? Any other questions? All right. Let's take a look at this one. So now we're finding the limit as t approaches 0. We've got square root of t squared plus 9 minus 3 all over t squared this time. All right, so again, first thing you want to ask yourself is, can we direct substitute? So what do we think? No, right? It's going to give us 0 squared in the denominator. That's not going to work. So now again, we have to think about a way that we might be able to simplify this so that we could then direct substitute. Any ideas on what we might be able to do with this one to simplify it this time? This one's not as obvious as the others. Okay, so I get that a lot, right? People want to square the numerator and denominator. Keep in mind, if you do that, then you change the value of it, right? So, just to kind of give you an example, like if you had 2/3, 2/3 squared would be 4 over 9. That's not equivalent to what we started with, right? So that's why we're not allowed to do that. Any other ideas? It is going to be a conjugate. Good, right? So if you remember back to pre-cal, right, to rationalize, usually we rationalize denominators, but in this case, we're actually going to try to rationalize the numerator so that we can get something in the denominator that we can actually substitute into. So what would be the conjugate of our numerator this time? So remember, when you're looking for conjugates, everything stays the same except for the sign between the square root and the number, right? So this is just going to be the square root of t squared plus 9, and then it's going to become a plus 3 on the outside instead, okay? Now, what we're going to do then is we're going to multiply, and remember, whatever you do to the numerator, we have to do the denominator, so we're going to multiply top and bottom here by that conjugate. So in general, if you have a square root like this, right, and you don't have any other way of simplifying, you can always multiply by the conjugate on top and bottom and see if at that point, once we simplify, if we can then direct substitute. So let's think about this one now. If we multiply that numerator, this is going to be FOIL now, right, because we have two terms up here, two terms over here. What's that going to give us if we multiply that out? Good, right? So this is just going to be t squared plus 9 minus 9. Because in this case, the whole purpose of using the conjugate is the outer and inner terms should cancel each other out. So we're really just multiplying these two square roots together, which is going to cancel out the square root and give us t squared plus 9. Then we're multiplying the negative 3 and the positive 3, which gives us that minus 9. And again, the outer and inner terms are going to cancel. Right now, in the denominator, I'm just going to leave this as is, as t squared times the square root of t squared plus 9 plus 3. Okay. You could distribute the t squared, but in general, your best bet is probably going to be to keep it factored like that, because in the end, we're hoping something's going to cancel out on top and bottom, so keep those factors like they are. All right, now, if we look at the numerator, what can we do at that point? Yeah, cancel out the 9, so that leaves us with t squared over t squared times the square root, t squared plus 9 plus 3. All right, what can we do now? Good, right? The t squared common factor in the numerator and denominator is going to cancel out. So now we're left with limit. So what do we have in our numerator now? 1, right? So don't forget, we still need that 1 up top. And then we've got the square root of t squared plus 9 plus our 3 down here. Can we direct substitute at that point? Yes, right? Because plugging 0 in for that t in the denominator will not give us 0 in the denominator anymore. So now we can just plug in. So we're going to get 1 over square root 0 squared plus 9 plus 3. And if we simplify that now, what's that going to give us? Okay, so we're going to get 1 over square root of 9 is 3, right? So that's a 3 there, plus this other 3, and it's going to simplify now to 1 over 6. Okay. Any questions on that? So again, if you ever see a square root and you have a function where you cannot direct substitute, look for the conjugate, multiply numerator and denominator by that conjugate, simplify, and then see if you can plug in at that point. All right, now this is something we already talked about in the previous section. Okay, we're just going to review it here. So the limit as x approaches a of f of x is equal to some L value. That's our limit, if and only if our limit from the left and limit from the right are the same value. Okay, so just keep that in mind. Limit from the left and right have to be the same. That's the only way the limit's going to exist. All right, so now we want to show that our limit as x approaches 0 of the absolute value of x is equal to 0. So they're telling us what it should be equal to. We just need to show the steps to prove that that's true. Okay. Now, we're not allowed to direct substitute here because this is not a polynomial or a rational function, right? It's an absolute value function. So we've got to think about a way that we can show that this limit is actually equal to 0 now. So any thoughts on what we might be able to do here? Okay, so think back to when we first looked at the absolute value function earlier in this unit. What did we do with our absolute value function? Okay, Haro?
So what? I don't know. What I would do is I would draw it out, right? Just I ignore the absolute, right? Because we know it's x, but we also have to know that it can't have a negative, and so we have to know that it can't go past negative. But anything above that is a go. So would the
Okay.
limit be in like? I don't want to say infinity because there's not infinity, but
So we know the limit should be equal to 0, right? So I'm good with looking at the graph, right? I still want to think of an algebraic way that we can prove this, right? But what would the graph of this look like?
it would just be linear.
Okay. All right, good. So it's going to be, remember, the V-shaped graph if you were to graph it. Okay, so it's going to have a point here at the origin. It's going to go up and to the right like this, and then up and to the left like this. Okay, and then like Dean said, we can think of this as a piecewise function of two separate linear functions. So let's rewrite our function now as a piecewise. What's the first piece of that piecewise going to be? Okay, you could use negative x, okay, and so it's going to be negative x whenever our x value is what? Less than 0. Good. Right, so whenever x is already negative, okay, we need to take the opposite of x, so that's going to be the left-hand side. What's the other piece of the piecewise going to be? Positive x. Good. And then what's the domain for that? Greater than or equal to 0. Good. So whenever x is greater than or equal to 0. So remember, that's how we split up our absolute value function into two separate linear functions that meet at the origin like that. Okay? Now, if we think about how we can show that this limit is equal to 0, remember on the previous slide we said that means that the limit from the left and the limit from the right need to be the same. So what I want to do now is think about those two individual limits and make sure that we can say that they are the same value. We're going to take our limit as x approaches 0 from the left of f of x. Well, if we're approaching from the left, which piece of our piecewise function are we using now? The negative x, right? Because now we're in the negatives. So we're going to say that this is equal to the limit as x approaches 0 from the left of negative x. Well, negative x is technically a polynomial function, right? So what can I do now? Plug in 0, right? Because we can direct substitute into anything that's polynomial. So this is just going to give us negative 0, which is the same thing as 0, okay? All right, so now we've shown the left-hand limit is equal to 0. Now we need to show that the right-hand limit is the same thing. So I'm going to take the limit as x approaches 0 from the right of my function. If we're approaching from the right, which part of our piecewise are we looking at? The x. Good. So now we're saying find the limit as x approaches 0 from the right of x. And again, x is a polynomial function, so we're allowed to direct substitute. And if we do that, what do we get? Just 0. Now, once we know the left-hand and right-hand limits, we can put that together, and that tells us then that our limit as x approaches 0 of f of x, which in this case is the absolute value of x, is indeed equal to 0 now. So basically, whenever you're asked to show that a limit is equal to something like that, you want to think about your left-hand and right-hand limits, and as long as you can show that both of those are the same, then we know that that limit is equal to whatever value you've got there. The only way we can do that in this case is to think of this as a piecewise function where we get two different polynomials, two different linear functions, so we can think about those limits individually. Any questions on that one now? Okay, at 0, Dean, right? So that's the only point. It's differentiable everywhere else except for that sharp point. Okay, but again, we'll get to that when we actually look at derivatives. Any other questions there? All right. So now we want to prove that the limit as x approaches 0 of absolute value of x over x does not exist. Okay, so in the previous example, they gave us what the limit was equal to. We needed to show that the left and right-hand limits were the same. If we're trying to show that this limit doesn't exist, what do you think we might want to do instead? All right, so you could sketch the graph, right? That's one way. We can't substitute, right, because that's going to give us 0 in the denominator, but don't assume that just because you get 0 in the denominator, your limit doesn't exist, because we've seen plenty of examples where initially we could not substitute 0, but eventually we got it to a limit, right? So you could sketch the graph, right? That's one way to kind of think visually about this, but I do want to do it algebraically also. What would we need to show if we want to prove that this limit does not exist? So think about how we showed that a limit did exist and was equal to a particular value. What could we show to prove that it does not exist instead? Okay, good. If we can show that the left-hand limit and right-hand limit are not the same value, then we know the limit doesn't exist. So we want to do the same thing we did on the previous example, except now we're hoping we don't get the same value from the left and the right. Okay, so that's what I'm going to do here. I'm going to take the limit as x approaches 0 from the left, absolute value of x over x, and then we're going to look at the limit as x approaches 0 from the right of that same function. As long as we can show that we get two different values here, then we know the limit does not exist. Now, think back to our absolute value function. If we're approaching 0 from the left, what is the absolute value of x going to be equal to? Negative x, right? So thinking back to how we broke it into a piecewise, this becomes the limit as x approaches 0 from the left of negative x over x. Whenever x is already negative to the left of 0, that means we're going to take the opposite of x in this case. Now, can we simplify that function now? Yeah, right? So what's negative x over x? Just negative 1. So now we're finding the limit as x approaches 0 from the left of negative 1. Well, what's our limit as x approaches 0 from the left of negative 1? Negative 1, right? Because anytime you're taking the limit of a constant, it should be equal to that constant. So this is just equal to negative 1. Any questions about how I got to that limit? All right, let's look at the second one now. So now we want to take the limit as x approaches 0 from the right. If we're approaching from the right now, what's our numerator going to become instead? X. Because now that absolute value of x is just positive x, since we're to the right of 0. And if we simplify this time, what are we going to get? Good, positive 1. So now we're looking at the limit x approaches 0 from the right of positive 1. And if we take that limit now, what's that going to give us? That's going to give us a 1. Any questions about how we got that? All right, now based off of that information, we looked at our limit from the left and from the right. And so now what can we say? So what's our overall limit? Okay, so we have two separate limits, right? And so the overall limit now does not exist, right? So because we broke it up, we looked at our limit from the left and the right. We did not get the same value for both. Now we can say that the overall limit does not exist then. So again, in general, if you're asked to prove the limit doesn't exist, that's one way to do it, is to show that the limit from the left and the right are not approaching the same value. Any questions on that one now? All right. All right, so now we got another piecewise function, f of x equals square root of x minus 4, wherever x is greater than 4, and then 8 minus 2x, wherever x is less than 4. Okay, so we want to figure out, does the limit as x approaches 4 exist? All right, so how would we determine if that limit exists this time? So think about how we showed that the limit did not exist on the previous example. All right, good, right? So we just need to look at the left-hand limit and the right-hand limit and show that they are the same. And if they're not, then we know it doesn't exist, right? And as long as they are the same, then we know it does exist. So if I think about my limit from the left and the right here, limit as x approaches 4 from the left. Start with that. How would I find that limit as we approach 4 from the left? Okay, good. From the left-hand side, we're using that bottom piece of our piecewise function because that's where x is less than 4. So now we're looking for our limit as x approaches 4 from the left of 8 minus 2x. Now, how could we find that limit? Yeah, now we can just substitute, right? We have a polynomial there. We're allowed to plug in the 4. So this is just going to give us 8 minus 2 times 4. What would that be equal to? That's just 0. Good. So there's our left-hand limit at 4. Now we need to look at the right-hand limit and see if we get the same thing. We're going to take our limit as x approaches 4 from the right. If we do that, which piece of our piecewise are we looking at? This time it's the top, right? So this is going to be the square root of x minus 4. Now, technically, we're not allowed to direct substitute here yet, okay, because this is not a polynomial or a rational function. Those are the only two that we've shown that we can do that for. But what are we allowed to do with square roots? Okay, we don't actually have to use a conjugate here because we're not going to get something that's undefined like we did on that other example. Okay, but just think about your law for our limits. What are we allowed to do with that square root? Good. Pull it outside, right? So in this case, we can rewrite this now as the square root of the limit as x approaches 4 from the right of x minus 4. Okay, so that was one of our limit laws. Whenever you have radicals like that, you're allowed to bring those outside of the limit and then just take the limit of what's inside instead. Well, now what's inside is a polynomial, so now we can direct suit. So what's that going to give us? 0, right? So we're going to get the square root of 0, and that's just equal to 0 now. So now we've kind of shown that if you have a radical like that, we can indeed just direct substitute like we have for polynomials and rationals, because bringing that square root out is not going to change anything. So we're allowed to just plug in directly. We could have just plugged in right there instead. Now, what did we just show then? Okay, good. The limit does exist this time, right? So since we got the exact same value from the left and the right, that tells us that our limit exists. And in this case, the limit would be equal to 0, right? It didn't ask us to necessarily find that. It just wants to know, does it exist or does it not exist? Now, another way to think about this, right, visually, you could graph each piece of this and then make sure that they actually meet at a point, right? So in this case, that point is going to be 4, 0. There's going to be an open circle there, right, because it's not defined for that point for either function, but you would get an open circle there at 4, 0. That's where these two functions would come together. Any questions on that one now? All right. We're not going to do greatest integer function. Okay, so here we go. If f of x is less than or equal to g of x when x is near a, right, so that's some x value, except possibly at that a value itself, and the limits of f and g both exist as x approaches a, then we can say that the limit as x approaches a of our f of x function is always going to be less than or equal to the limit as x approaches a of g of x. Okay, so basically, as long as one function is always below another function, right? That's what it means for one function to be less than or equal to the other. Then we know that our limit, as we approach some specific a value, has to be less than the other one for f of x versus g of x. Okay. Now, the reason that theorem is important is to be able to show the second theorem. Okay, so the squeeze theorem is really the more important one. If we have three functions now, f of x, g of x, and h of x, where g of x is now always in between f of x and h of x. Okay, so h of x is always going to be the biggest, f of x is always going to be the smallest, and g of x is just somewhere in between there. If we know that, then we can say that the limit as x approaches a of f of x equals the limit as x approaches a of h of x equals some limit, right? If that's true, then the limit as x approaches a of g of x has to be the same value. And you can see that on the graph down here. So here's our a value that we're approaching. As long as the h of x is approaching some L value and the f of x is approaching some L value, and if we know that g of x is always in between those two functions, as long as they're approaching the same value, then g of x also has to be approaching the same value. That's what the squeeze theorem tells us. Any questions about that theorem? Now, the reason this is useful is sometimes we'll end up with functions where calculating the limit is not easy, or it might even be impossible just based off of the properties of limits that we know. But if we can somehow say, well, we know that this other function is always bigger than the function we care about, and this other function is always smaller than the function we care about, if we can show that both of those limits approach the same value, then we know that our function that's between them has to approach that same value also. Okay, so that's how we're going to use this. All right, so let's take a look at this example. We want to find our limit as x approaches 0 of x squared times the sine of 1 over x. We're trying to show that that's equal to 0. So they tell us what the limit is. We need to prove it now. All right, now, technically we have a property where we can split up multiplication, right? The problem with doing that here is if we split it up and take the limit as x approaches 0 of x squared and multiply it by the limit as x approaches 0 of sine of 1 over x, the sine of 1 over x at 0 is undefined, so that's why we're not allowed to just split this one up, right? We're not going to be actually evaluate it that way. And then there wouldn't be a way to simplify the sine of 1 over x to be able to direct substitute either. So we've got to think about this in terms of functions that we're familiar with and see if there's a way that we could somehow squeeze this function between two functions that we know the limit of to show that this limit has to be approaching 0 now. So here's what I'm going to start with. I'm going to start with just the sine of 1 over x piece. Now, what do we know about sine of 1 over x in terms of its possible values? And you can ignore the 1 over x piece, right? Just the sine function in general. What do we know about it? Okay, good. It's always between -1 and +1, right? And in this case, because we're not multiplying by anything, right? This isn't stretching it vertically. We know that this sine function, even though there's a 1 over x in there, is still going to be between -1 and +1. So I'm going to write this as -1 is less than or equal to sine of 1 over x, which is less than or equal to 1. Because I know that sine function now has to be between -1 and +1. Now, what we care about, though, is the x squared times sine of 1 over x. So what I want to do now is get that function in the middle so that it's squeezed between two other functions. What would I need to do with this function now to make it look like the one we started with? If I want this function right here now, what would I need to do with what I've got? So what's missing? The x squared, right? So that's the only thing that's missing now, right? I've got my sine of 1 over x. I need the x squared piece. So all I'm going to do now is I'm going to multiply this by x squared. If I do that, I have to make sure that I'm doing that to all three pieces of this inequality now. So I'm going to come over here, multiply this by x squared, come over here, multiply this by x squared. Now I'm allowed to do that because x squared is definitely going to be positive, right? And so I'm not going to need to worry about flipping any signs or anything. So when I simplify this now, I get negative x squared is less than or equal to x squared times the sine of 1 over x, which is less than or equal to positive x squared. Any questions up to that point? Okay, now, remember, we're trying to show the limit as x approaches 0 of that function in the middle is equal to 0. Well, now I have these two functions, one that's always less than or equal to the function we care about, and one that's always greater than or equal to the function that we care about. So using the squeeze theorem, if I can show that both of those have a limit of 0 at 0, then I know that the function in between also has to have that same limit. So now we just need to find each one of those limits. So I'm taking the limit as x approaches 0 of negative x squared, and the limit as x approaches 0 of positive x squared. Well, what can we do to find the limit as x approaches 0 of negative x squared? Substitute, right? It's a polynomial. We can plug in. It's going to give us negative 0 squared, which is just what? 0, right? So this gives us a limit of 0. Down here, same thing. We can substitute because it's a polynomial. We get 0 squared, which is also. Okay? Now, based off of that, and now knowing that that function that we care about is between those two values, this tells us then that our limit as x approaches 0 of x squared times the sine of 1 over x is indeed equal to 0 now. So that's how we apply the squeeze theorem, right? It's not the easiest thing in the world to see, right? But if you can look at your function that you start with, right, and you have something where you cannot direct substitute, but you can somehow break that function down into something where you know the range of the function. In this case, trig functions are always the ones that stand out, because we know sine and cosine are always between -1 and +1. Then we can start to try to get the function that we started with from that inequality, and then look at our limits on the left and the right, and then say, okay, that function in between then has to have that same limit. Okay? Any questions on that one now? Yeah, Hara.
Are the two that you're comparing, are they always going to be like equal, like to each other? Like in this case, both of them were 0, 0. But what if we had a case that was like
if the question is asking you to show that a limit is equal to something, then yes, right? If it's just saying like find this limit if it exists, then it's possible that you won't be able to get the same limit on both sides. And in that case, you would just have to say, well, that limit must not exist then, right? But in this case, because they're telling us specifically, yes, show that it's equal to 0, those two functions should give us a limit of 0 so that we can then squeeze the one in between and say that limit's also 0. Okay? Any other questions there? Ira?
Is there another way besides using this squeeze theorem to solve this question?
Not really. Just because, like I said, the sine of 1 over x piece is undefined to begin with, and you're not going to be able to rewrite it in any way to where you could actually do a substitution here. So for this one, squeeze theorem is pretty much the only option. Okay. Now, obviously, you could look at your graph too, just to kind of see what it looks like the limit is approaching, right? It's going to be undefined at 0, but you should be able to look at the graph and see, oh yeah, it's actually getting close to that value. Let me actually switch over to Desmos real quick and just show you kind of what we've done here, because I think that picture helps a little bit. All right, so what we were looking at in this case was the function x squared times the sine of 1 over x, right? we wanted to show that our limit as we approach 0 is equal to 0. Well, if you look here, right, when you zoom in, this thing gets really, really flat, right? These oscillations get really close together as we get close to 0. We can still trace, right, and we can see that those values are indeed getting closer and closer and closer to 0 as we go, right, from the left and the right. But what we've really done now, we're looking at the function x squared and negative x squared, and you can see that that function is always between positive x squared and negative x squared. And we know that both of those functions have a vertex at the origin. Therefore, that other function's always between them. Right, and I'll zoom out so you can see how it always just oscillates between those two. Okay, that function there also has to have that same limit now. Okay, so again, visually, graphically, that's how we would look at that. But yeah, algebraically, other than squeeze theorem, there's not really another way to think about this one. Hyro?
So for this case, signed was like normal, so it had the range of -1 to 1. Would there be a case where it would have like a shrink or a stretch that would have to use, and we'd have to find the range comparing those?
It could, right? So yeah, so remember we talked about our transformation. So if there was like a 3 times that sine function instead, then we know that that stretched vertically by a factor of 3. That means that that sine function would always be between -3 and +3 instead. You could actually have some that are translated up or down also, right? So if you're adding or subtracting something to the sine function, then it could actually shift it up or down. That would also affect that range of values. So you'd have to think about that. Now, I'm not going to give you anything that complex, right, on a test especially, but just know that it is possible to do that, right? If you had a translation or some type of transformation like a vertical stretch, you could just reset your range between those two values and then still, figure out what functions you're between and then apply the squeeze theorem that way. Other questions there?
Oh, I do. So when we're using the squeeze theorem, we're using the range, and that's what we're comparing.
That's right. Yeah. So if you have part of your function that you're looking for the limit of that we know has a set range, right? That's not like negative infinity to positive infinity. That's what's helpful, right, when we're applying the squeeze theorem. Okay. So like I said, usually it's those trig functions that always stand out. If you've got one of those in there and you don't have another way to find that limit, think about the squeeze theorem, think about the range of values for that trig function, and then see if you can get the actual function that you care about from that. Okay. Any other questions? All right, so I know we're past break time. Let's take a break. We'll come back at 11, let's just call it 11:20, and then we'll use the last 30 minutes to get started on section 1.8. All right. So like I said, this is section 1.8 continuity. So what we're going to look at here is what does it mean for a function to be continuous? How do we find intervals where a function is continuous? And then how do we find any discontinuities that it has, right? Where is it discontinuous? The reason this is important is because there's a lot of things we're going to do later where a function needs to be continuous to be able to actually do those processes. And so we need to understand what does it mean for a function to be continuous and how do we figure out where it is. Right, so continuity. A function is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. Okay, so there's three things that we're going to check for continuity here. Number one, we have to figure out, does f of a actually exist, right? So is there a defined point at f of a? Then we're going to look and see that the limit as x approaches a exists. So we need an actual limit at that point. Then once we know that those two things are true, then we can see if the limit as x approaches a is equal to the value of the function at that point. Okay, so you got to have a defined value, the limit has to exist, and that defined value has to be equal to the limit. Okay, those are the three things we're looking for now. Okay, so in other words, if you look at the graph over here, okay, we have our limit as we're approaching from the left and the right, that's equal to this f of a value. The function itself is defined at that point, and those two values are the same, therefore the function is continuous. Okay? If any one of those three things breaks down, then we have a discontinuity there. Okay. All right, so what we want to figure out here is where do we have discontinuities? Where is this function discontinuous? And then we're going to use one of those three justifications for why it's discontinuous there. So looking at this graph, where is one place that we have a discontinuity on this graph? Okay, so at 5, right? So at 5, x equals 5 has a discontinuity. So now we need to explain why there's a discontinuity there. Okay, so number one, right, we have to have a defined value at that point. Do we have a defined value at that point? Yes, right? So if you look here, right, there is a point at 5, therefore it is defined for some value at 5. The second criteria is the limit has to exist. Do we have a limit at 5? Yes. So as we approach from the left and as we approach from the right, okay, we are approaching some value, okay, and it is the same from the left and the right, therefore that limit exists. Okay, so we meet the first two criteria. The third criteria is that the limit has to be equal to the value of the function. Is that true here? So is the limit at 5 equal to the value of the function at 5? So I know there's no actual values on the y-axis over there, but think about what this limit would be equal to, and then think about what the function there is equal to. They're not the same, right? The limit is approaching this value. The value of the function is this point up here. They're not the same, right? So in this case, we can say that there is a discontinuity at x equals 5 because the limit as x approaches 5 of our function f of x is not equal to the value of the function at 5. So f of 5 is not equal to the limit at 5, therefore there's a discontinuity there. Pyro?
Okay, so what we've been doing before, um, it's been like a discontinuity, right? Because there's limits on like coming in, right? But as a whole, there's not a limit because it's a discontinuity. correct, or is that a different definition?
Okay, so we have to be careful here, right? Because if the limit from the left and the right are not the same, then we know there's no overall limit, right? As long as the limit from the left and the right are the same, then the limit exists. And that's what we have here at 5, right? The limit from the left and the limit from the right are the same value. That limit does exist, and it's equal to whatever this point is right here, right? And again, I don't have y values on the axis to say it's equal to this specific number. Okay, but it's whatever that y value would be. The value of the function this time, though, is this point up here, right? Because that's how the function is defined. So the problem with this one, the reason we have a discontinuity here is because that limit is not the same as the actual point that's defined for the function. So the limit exists here, but it's not the same as the value of the function. Does that make sense? Okay. Any questions on that one now? Okay. Where else do we have discontinuities on this graph? Okay, there's one at 1. So let's look at the one at 1 first. So x equals, x equals 1. All right, so again, we're going to go through those 3 criteria, right? If we go through the first one, right, we need the function to be defined at 1. Is that true here? No, right? So it fails the very first criteria. So we can just say in this case that f of 1 does not exist. And that's justification enough to say that it's definitely not continuous there. Okay. Any questions on that one? All right, and then some people said 3 as the last discontinuity. That's right. So x equals 3. All right, so again, go through your criteria. Is f of 3 defined? Does it have a defined value? Yes, right? Now we need to think about the limit. Does the limit as at 3 exist? It does not, right? And why does the limit not exist this time? Okay, good. So as we approach the left and the right, in this case, right, I'm approaching 3 from the left, approaching 3 from the right. They're going to 2 different y values. So we can say that this limit as x approaches 3 of f of x does not exist. Okay? Again, you just need to show that one of those 3 things doesn't work, and that's justification enough for this to be discontinuous there. Again, the 3 criteria: function has to be defined at that point, limit has to exist, and the limit has to be equal to that defined value. Those are the 3 things we're looking for. Any questions on that one now? Yeah, let me go back. Sorry. So the x equals 1. Okay, in this case, we just have an open circle at 1. There's no other defined point there, right? So at 5, we had this other point up here. So 5 was actually defined. So all we can say with that first one, if the function's not even defined at that point at all, then we know it's definitely not continuous there. Okay, so if you just open circle, then it's automatic, right? No other point, then we automatically know it's discontinuous. Okay. Any other questions? All right. So let's take a look at example 2. So now we want to figure out where are each of these functions discontinuous. And we're not given the graphs this time, we're just given the functions themselves. So we've got to think about where we're going to have a discontinuity. All right, so if we look at the first one here, we have this rational function. How do you think we would find discontinuities for that function? Okay, good. So what do we know about the denominator? What restriction do we have? Okay. All right, good. If that's equal to 0, there's going to be a discontinuity there, right? So we can never have 0 in the denominator. So if we set the denominator equal to 0, that's going to tell us where we're going to have a discontinuity. So I'm going to say x minus 2 cannot be equal to 0, which means that x can't be equal to what value? 2. Good. Okay, so that function is not defined at 2. Therefore, there's going to be a discontinuity at x equals 2. And the reason for that is that f of 2 does not exist. Okay. Any questions on that one? And just keep in mind, right, if you had more than just that x minus 2 in the denominator, right, then you could always factor if it's possible, things like that, but always set it not equal to 0, figure out what your restrictions are on your domain, and if you know the restrictions on the domain, now you know there's discontinuities there because the x value can't be equal to anything at that point, okay? All right, let's look at part B. So now we've got piecewise function 1 over x wherever x is not equal to 0, and then it's equal to 1 where x is equal to 0. All right, so we know the function, first off, needs to be defined at a value, right? So is this function defined for all values? Yeah, right? So it's 1 over x wherever x is not equal to 0, and it's equal to 1 if x is equal to 0. So we're defined for every x possible value, right? The second criteria is that our limit has to exist, right, at all of our values. Is there anywhere where our limit might not exist that we might want to check? Yeah, so we need to check 0 and see if our limit even exists there, right? Because if we don't have a limit, then we know it's going to be discontinuous at that point. So let's think about our limit as x approaches 0. How would we find the limit as x approaches 0 here? Yeah, right. So we're going to have to almost do a table of values, right? And think about from the left-hand side and the right-hand side, what values are we approaching? Okay, because in this case, we can't direct substitute. That would give us 0 in the denominator. There's no way to simplify 1 over x either. Okay, so if we think about that now, from the left-hand side, right, if I'm plugging in values smaller than 0 in the negatives now, what's happening to 1 over x as I substitute those values getting closer to 0 on the left-hand side? It's going to negative infinity, right? So if you wanted to, right, just kind of real quick, if you put in like negative 0.1, negative 0.01, negative 0.001, and so on, we're plugging into 1 over x right here. As you do that, those values are going to get infinitely big in the negative direction. And so this is now approaching negative infinity. Okay. Now, what if we look on the other side and we do some values on the positive instead? So 0.1, 0.01, 0.001. What value are we going to be approaching on that side? Positive infinity instead, right? So these are going to get infinitely large in the positive direction, and so those are approaching positive infinity. So what can I say then about that limit? Doesn't exist, right? Because one side's going towards negative infinity, the other's going towards positive infinity. In this case, that limit does not exist then. If the limit doesn't exist, then what does that tell us about zero then? It's discontinuous there, right? So x equals 0 is a discontinuity. Okay. And it does not matter in this case that it's defined at 1, right? Because all we care about, right, is it defined for all values? Does the limit exist at all values? And in this case, that limit doesn't exist at 0, so there's no point in checking to see if the value of the function is the same now. Any questions on that one? Okay, let's look at C. So now we have a piecewise function. This time the top piece is the same as the original f of x function we started with in part A, but we do have this defined value now at x equals 2. So we can't use that justification now that f of 2 doesn't exist, because f of 2 does exist this time, right? It's equal to 1. So what do we need to check now to see if we have a discontinuity for this one? So let's start here. Where's the only place we might have a discontinuity? At 2, right? So just like part A, we had a discontinuity at 2. That's the only place we have to worry about. Now, we know in this case that the function's defined, right? So we can't use the same justification that we used in part A. The next thing we would need to see is, does the limit exist at 2? Let's check that. So I'm going to find the limit as x approaches 2. And in this case, remember we said, as long as it's defined for all values around 2, we're going to use that top piece of the function to evaluate that limit, right? It doesn't matter that it's some other value at 2, because we're only looking from the left and the right anyway. So we're just looking at the x squared minus x minus 2 over x minus 2 up here. Now, can we direct substitute? No, right? It's going to give us 0 in the denominator if we do that. So what do we want to do now to see if we can factor? Good. So let's factor this, simplify it, see if we can direct substitute to find a limit. What would be the factors of our numerator this time? Good. X minus 2 and x plus 1. We still have our x minus 2 down here. So now if we simplify that, we're finding the limit as x approaches 2 of what? Good. X plus 1. And now if we find that limit, what is that limit going to be equal to? 3. Perfect. Now, that means that the function is defined at 2. The limit does exist. So the third thing we need to check for now is the limit equal to the value of the function? What do we think? It is not, right? The value of the function this time at 2 is 1. The limit that we got is 3. Those are not the same value. So x equals 2 is still a discontinuity. But this time the justification is that f of 2 is not equal to the limit as x approaches 2 of our function. So again, when you have piecewise functions like that, right, you got to think, first off, is it defined at that point? In this case, yes, it is. Then you got to think, does the limit exist at that point? In this case, yes, it does. And then we have to check, does that limit equal the same thing as the value of the function? In this case, that's the thing that breaks down, and that's why we can say there's a discontinuity there. Any questions on that one? We're not going to do the greatest integer function, so you can just ignore that one. Okay, just know, right, that's the step function, so it would have a discontinuity at every integer, right, because it's going to jump at all of those, so those limits are not going to be the same from the left and the right. Okay, but again, I'm not going to ask you to do anything with that on the test. All right, so types of discontinuity now. There's 3 basic ones that we've looked at, right? And that's what we're going to define here. So in parts A and C that we just looked at, those we'll call removable discontinuities. And the reason we call them removable is because all we would have to do is fill in a single point and it would be continuous. Okay, so if you ever have a function where it's really just an open circle, right, the function's not defined or the limit is not the same as the defined value, all you have to do is redefine that value, fill in that hole, and all of a sudden it becomes continuous. Okay, so that's what it means to be removable. Part B, though, where we had that asymptote where it's going to infinity on one side, negative infinity on the other, or it could even be going in the same direction on both sides. Okay, but if it's going to infinity or negative infinity, we call that an infinite discontinuity. The reason there's no way that I can just fill in a single value and make it continuous, right? It's not just a hole in the graph now, it's an actual asymptote. So there's no way to define a value that would then make it continuous. And then the last one is what we call jump discontinuities. And again, that's what the greatest integer function would have. So just to kind of give you a picture here, right? We'd have defined values here. It would jump. It would jump. It would jump, right? And so on. Okay, so you get these series of horizontal lines, segments, okay? And those are what we call jump discontinuities. Again, they're not infinite, but we also can't just fill in a point to make them continuous. And so we have a third type, which we call jump discontinuities now. Any questions on those 3 types? Okay, and then here's the graphs of each one of those. Okay, so again, that first one, the graph of the first function that we looked at would look like this. There is an open circle right there at 2. Okay, and so that's what we call a removable discontinuity, because I could just fill in that one point and all of a sudden that function becomes continuous. Second one here, this is our infinite discontinuity because there is no way to actually just fill in a single point and make it continuous. It's going to infinity. Oh, sorry, this one, I had 1 over x. They gave 1 over x squared as their example. That's why it's going the same direction on both sides. Okay, so that's why it's different from what we saw in our example. The next one here, again, is another example of removable, because I could just fill in, sorry, that one open circle right there, and that would make it continuous. And then the last one is that step function, greatest integer function. That's a jump discontinuity. All right, now, a function f is going to be continuous from the right at a number if the limit as x approaches a from the right is equal to f of a. Okay, so it is possible to not have continuity overall, but just have continuity from the left or continuity from the right, just like we have limits from the left and limits from the right. And then if it's continuous from the left, that means that the limit as x approaches a from the left is equal to the value of the function there. This is useful in a lot of cases where you have jump discontinuities, and you just want to look at your limit from the left or from the right and think about whether it's continuous in either of those directions now. It also helps if you have a function that's just on a certain domain, then you can think about continuity either from the left or the right if it doesn't go to infinity or negative infinity. Okay. Yeah, so Rachel, just remind me at the end of class and I'll be happy to answer a question about the test. Any questions about continuity from the left or the right? All right. Again, I'm not going to do that one. Okay. So a function f is continuous on an interval if it is continuous at every number in that interval. Okay, so basically, if f is defined only on one side of an endpoint of an interval, we understand continuous to be continuous from the right or continuous from the left. So just understand here, as long as it's continuous everywhere within that interval, then it's continuous. But if we just say it's continuous, but it's only defined on one side or the other, then we understand that means continuous from the right or left. All right, so what we want to show here is that this function is continuous on the interval from -1 to +1. All right, so keep in mind, to show continuity, right, there's three things we have to show. One, it has to be defined for all the values in the interval. Two, the limit has to exist for all the values in the interval. And then three, the limit at all of those values has to be equal to the value of the function at all the points in the interval. Okay, those are the three things we have to show here. So first off, if I want to prove, just show here, that this is defined for all values in this interval, how could I do that? Okay, good, right? So basically just figure out what is the domain of this function in general, right? And as long as -1 to 1 is in that domain, then we're fine, right? How would you find the domain of this particular function now? So if you have a square root as part of your function, okay, good. Whatever's inside the square root can't equal anything less than 0, right? So it has to be greater than or equal to. So what I'm going to do is I'm going to take the 1 minus x squared that's inside the square root, and I'm going to say that it must be greater than or equal to 0 now. Now, to find the domain from there, right, what would you do? Okay, if you move the x squared to the right, then you'd have to take a square root and you'd end up with a plus or minus. It's difficult to determine which way the signs are going to go, right? So factoring is going to be our best bet here. This is the difference of squares. We're going to get 1 minus x times 1 plus x greater than or equal to 0. Now, just for sake of time, I'm going to try to finish out just the domain piece, right? And then we'll come back to it tomorrow and finish out the rest. I'm going to take my 1 minus x now, set it equal to 0, 1 plus x, and set it equal to 0. which is going to give us two numbers that we're going to use for a number line. So we're going to get x equals 1 and x equals -1 here. If you remember back to your pre-cal days, right, this is how we figure out where it's actually positive and negative and where this thing is actually going to be greater than or equal to 0. So we need to pick some test points here. I'm going to go with -2 in that interval, 0 in that interval. We'll go with 2 in that interval up there. Now it's up to you where you plug it in, right? Either back in the original or the factored form, it does not matter. If I do 1 minus -2 squared, -2 squared is 4. 1 minus that is going to give us a negative value for that interval. And then I'm plugging in 0 again right up here. 1 minus 0 squared is just 1, so that's going to give us a positive value. And if we plug in 2, 2 squared is 4. 1 minus 4 is -3, so that gives us a negative value for that interval. And because I want this to be greater than or equal to 0, that means I need it to be the positives here. That means my domain is everything between -1 and +1 inclusive, because it was greater than or equal to. Okay. So that right there shows now that the function is defined for all the values between -1 and 1. That's the first step. Okay. Like I said, we still have to show the limit exists and the limit's equal to the value of the function. Okay, but that's the first part, is just showing that the domain proves that it exists for all those values. Okay. Like I said, we'll finish up the rest of this section tomorrow and take some time to go through the practice test. You can go ahead and start reviewing if you want to. That way you kind of know which questions you might have questions about. Otherwise, just make sure that you get the 1.5 to 1.8 homework done by midnight tomorrow night, and then make sure that you have a time set aside to sit down and take your test sometime between tonight at midnight and Friday at midnight. Okay? Let me know if you got any questions about anything. Otherwise, great afternoon, and I will see you all tomorrow. All right, so test is due by midnight on Friday night. Okay? Like I said, it'll open at midnight tonight, and then you've got 48 hours to find a 2-hour window to sit down and take it. Okay? Yep.